So summary of group 2, do you notice that we either have graphs that have an x over x, or there's an x squared over x squared? In other words, that the degree is the same on the top and the bottom of our fraction. Characteristic. We have both horizontal and vertical asymptotes. Now the vertical asymptotes, those ones are easy because that's always your non-permissible value. X equals 1, x equals plus or minus 2. Notice in this second one that you could factor the top and the bottom, but nothing cancels out. Because if something canceled out, you would have a hole in your graph. And the third one, even though you can factor it, it doesn't cancel out. So there's nothing you can do for holes in that one. And every time after you factored it, if it doesn't cancel out, whatever's on the bottom will become vertical asymptotes. For the horizontal asymptote, what you can basically do is say to yourself, as x gets really, really big, that's when our graph starts to approach an asymptote. Either really, really big positive numbers or really, really big negative numbers. And as things get really, really big, the only thing that's going to affect it are the values with the highest degree. I don't know if you've ever played Monopoly and near the end of the game, if someone owes like $4 rent, you're like, yeah, I don't need that now because I'm dealing with hundreds and thousands of dollars. $4 doesn't make a difference. And that's basically what's happening in an equation like this first one. If x is in the thousands or the millions, will subtracting 1 on the bottom really make a big difference? No. So what we do is we sort of ignore all of the stuff that doesn't go with the highest degree. So here, the highest degree on the top was a 3x. The highest degree on the bottom is an x. And if you simplified 3x over x, you would just get 3, and that becomes your asymptote. In fact, if you look back at your original equation here, it's going to get, if this is a million, I'm going to have 3 million over almost a million, which will be really close to 3. And if it was a billion, you'd have 3 billion over almost a billion, which would basically be 3, but not quite. And so that's why we have an asymptote at y equals 3, because it's going to keep getting closer and closer to it, but never equal it perfectly. For the second one, what's the highest power on the top? An x squared. What's the highest power on the bottom? We have a term with an x squared. X squared over x squared is going to be 1. And so that's how we can tell the vertical asymptote in that second one is going to be 1. Third one, highest power on the top is an x. Highest power on the bottom is an x. On the top, we have the term is a minus 2x. On the bottom, the term is an x. If you simplify that, you're going to get minus 2. The nice thing about factoring each of these is you can easily find the x-intercepts. Because if the fractions are factored, and I factored the second two, and the first one's 3x is as close as you can get to factoring, the only time a fraction is equal to 0 is if the numerator, or the top of the fraction, is equal to 0. When is 3x equal to 0? When x is 0. So we have that as one of our x-intercepts. What about this one? When is that fraction equal to 0? When is the numerator equal to 0? At positive 1 and negative 1. So you have those two x-intercepts. And the last one, when would the top be equal to 0? When x equals 2. And sure enough, that shows up on our graph. So for a graph like this, we're going to draw both of our asymptotes when we graph it by hand. We're going to find as many x-intercepts as we can. Then we're going to draw the graph so that it approaches the asymptotes. And often we'll have to find another point by just plugging it in like a table of values and finding another point. So this is group 2. Group 3.